Hello viewers, welcome to my channel KK Concepts of Electrical Engineering. Polarization. In the previous videos, we have seen that uniform plane wave traveling in a positive x direction, the electric field E and the magnetic field H lies in the planes perpendicular to the direction of propagation. Each E and H can have components in other two directions. Thus, E can have components of EY as well as EZ. Similarly, H can have components in HY and HZ. Polarization means the time varying behavior of the electric field intensity vector E at some fixed point in a space along the direction of propagation. If the wave is traveling in the x direction, the components EY of E in y direction in perpendicular plane and the component EZ of E lies in the z direction in another plane which is perpendicular to both these planes. If the space wave is sinusoidal, the variations of EY and EZ with respect to time are also sinusoidal. EY and EZ may be equal or unequal in magnitude, and they may be in phase. There may be a phase difference between them. Accordingly, the tip of the total field intensity vector E would trace a straight line or a circle or ellipse on a plane which is normal to the direction of propagation of wave. Hence, the polarization of a uniform plane wave may be a linear, circular, or elliptical. First, we'll see the linear polarization. Consider uniform plane wave traveling in a x direction. Then let E denoted electric field having the components of EY and EZ. You can observe in the figure the pink color along which is in XY plane flowing like this, and EZ in blue color which is in XZ plane. Let EY equals to EZ in magnitude. That means the amplitudes are equal and they are in the same phase. When EY starts at 0, EZ also starting at 0. When EY is peak, EZ also peak. Since EY, EZ are in phase, they pass through the 0 in the same direction at the same instant and reaches their positive and negative maximums simultaneously. This is vector E is given by EY plus EZ vector sum. Since this is EZ and this is our EY, you can write this as EY UY along EZ along EZ is our E. Tan theta equals to, in this I have considered this is the angle theta, so tan theta equals to opposite one, that is EY divided by the adjacent side, that is EZ, where theta is the angle made between EZ and E. So in the figure you can observe linear polarized wave, the ratio of EY by EZ is constant at all the points. The field vector E is inclined by the same angle theta, theta tan inverse EY by EZ to EZ plane. The vector E appears to oscillate along a vertical line in a plane held perpendicular to the x direction. So when you observe this in the figure, at 0, both are 0, again 0, at 2 pi, again 0. In between, we have, this is our EY and this is the EZ. Here, this is our EY, this is our EZ. But when you observe from this side, at this point, the E value will be a dot. At this point, the E value YZ plane. Is again a dot. Is again a straight line. Again a dot. So in between, this is it. 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 So when you observe this resultant E from this side, you will find that E is oscillating from 0 to maximum of EY plus EZ as a straight line. So we say this type of polarization is linear polarization. So for the linear polarization, the condition is EY equals to EZ in amplitude and in phase. Circular polarization. Now circular polarization is going to occur when EY equals to EZ in amplitude and the phase difference is 90 degrees. If you observe this waveform, when a blue one, EZ is 0, the EY is max, and when EZ is max, EY is 0. The same thing is going to repeat again and again. When you trace the tip of E, the resulting E, we know that E equals to EY plus EZ, vector sum at 0, EY is max and EZ is 0. Pi by 2, EZ is max, EY is 0. And this thing is repeating again and again. When you observe this from this side, the wave is going to look like 0 with the peaks here and here, here and here. It will be a complete circle. Trace of tip of E. So the trace of tip of E is a circle. So this polarization is called circular polarization. To get the circular polarization, the condition is magnitudes must be equal, but the phase difference is 90. Elliptical polarization. Now if you observe these waveforms, pink one belongs to EY and blue one belongs to EZ. You can observe that EY is not equals to EZ. This is having more amplitude than this one. Phase shift is 90 here in this case, or you can take any phase difference. The resultant E equals to EY plus EZ. By looking from this side, you can draw this. EY is less than EZ. So if you observe, this is the magnitude of EZ, and if you observe, this is the magnitude of EY, then by tracing the tip of E from one side, we will get an ellipse, not the circle. The center of the ellipse lies on the OX axis, and the directions of the major axis and minor axis depend upon the magnitude of vectors and the phase angles between them. We have seen types of polarization. First one is linear polarization, in which the condition is EY and EZ equal or unequal in magnitude, but phase difference must be equal to 0. This is the condition for linear polarization, and here the tip of the trace for linear polarization will be like this. Circular polarization, this is the condition that both amplitudes must be equal and phase difference must be 90. But for elliptical polarization, magnitude must not be equal. The phase shift may be 90 or any other angle.
If you have any suggestions and queries, please mention in the comments. If you like this video, please like, share and subscribe. Thank you for watching the video. Please stay tuned for more videos.